Hi everyone, today's presentation is about sinusoids with topics of sine and cosine functions, complex numbers, phase and time shifts. The presentation will be through examples and visualizations for better understanding of the concepts. The channel offers subjects of communication systems, signal processing, control systems, AI, and IT. If these courses are of interest to you, please subscribe and share with your colleagues, friends and class fellows. The trigonometric functions, sine and cosine, belongs to the general class of signals used for modeling and interaction with systems. The mathematical form of a single sinusoidal signal is defined as x of t equals a cosine of omega naught into t plus phi, where a denotes the amplitude, omega naught equals 2 pi, f naught is the frequency in radians per seconds, and phi is the phase angle in radians. The pattern repeats itself after every 1 by f seconds, and this interval is known as the period of xt. The typical scenario to explain sine and cosine functions is depicted in the figure. The right-angle triangle, formed in the first quadrant, has sides of lengths x and y, and hypotenuse r. The cosine of the angle theta is defined as the base x divided by the hypotenuse r, and the sine of the angle theta is defined as the perpendicular y divided by the hypotenuse r. The variations of sine and cosine functions with angle are shown. The graphic shows how a point of distance r and angle theta in the first quadrant of the xy plane is related to the x and y coordinates of the point, that is, the pair x, y equals the pair of r, cosine of theta, and r, sine of theta. Note that the function plots are identical in shape, with the sine plot shifted to the right by 90 degrees, that is, the sine function is a delayed version of the cosine function. We also observe that both waveforms repeat every 2 pi radians. Additionally, the amplitude of each ranges from -1 and 1. An example plot corresponding to x, t, equals 10 into cosine of 2 pi 440 tons, 0.4 pi, that is, 440 Hz frequency, or a time period of 1 by 440 equals 2.27 milliseconds is shown. The waveform repeats after every 2.27 milliseconds, that is, time between two consecutive maxima, or minima, or zero crossings is the same. Few key properties and trigonometric identities are given in the tables. Some of the important identities include the equivalence between the sine and cosine functions, periodicity, and so on. It can be seen that both functions, in general, repeat after 2k by radians, where k is an integer. The cosine is even function, while the sine is odd. The derivative of sine function is the cosine, and that of the cosine function is negative of the sine. Some properties are also shown. Using properties 1 and 2, the properties 6 and 7 can be obtained. Similarly, 2 and 3 can be obtained from 5. An example is given for different angle scaling. The left side can be extended using 5, and the addition of the first two equation results in cosine of 9 theta plus cosine of 7 theta, which equals 2. Cosine of 8 theta into cosine of theta. Finally, cosine of 8 theta can be calculated using cosine of the three angles, that is, 9 theta, 7 theta, and theta. A complex number is an ordered pair of real numbers denoted as z equals pair of x, y. The first number, x, is called the real part of z, and the second number, y, is called the imaginary part of z. For algebraic manipulation, the ordered pair is written in the rectangular form as z equals x plus iota y equals x plus jy, where iota equals j equals square root of -1, that is, iota or j square is equal to -1. The corresponding polar form is written as z equals r, and the angle theta equals r, exponential with power j theta, which equals absolute or modulus of z multiplied with exponential of j multiplied with the phase angle. We can plot complex number as a vector, x, y, as shown below. The next figure shows four complex numbers z equals 2 plus j5, z equals 4 minus j3, z equals minus 3 minus j3, and z equals minus 5 plus j0. We can also draw the phases using the polar form by drawing a vector of magnitude r, subtending the angle with x-axis. For complex numbers z1 equals x1 plus jy1 and z2 equals x2 plus jy2, we define or calculate the sum as adding the real part of z1 with the real part of z2. Similarly, imaginary parts are added together. The same rules apply for the difference of z1 and z2. The product and quotient operations of z1 and z2 can be seen. The magnitude or modulus of the complex number is the absolute value, and is the distance from the origin in the complex plane. While its angle or argument is the angle which the number forms with the positive real axis. To find the absolute value of a complex number, we take the square root of the sum of the squares of the real and imaginary parts, which is a result of the Pythagorean theorem. The angle of a complex number is found by taking the inverse tangent of the ratio of imaginary part to real part. The complex conjugate of the complex number z equals x plus j, y is given by x minus j, y, which is a reflection of z about the real axis. To convert from polar to rectangular form, we can use simple trigonometry to show that x equals r cosine of theta and y equals r sine of theta. The rectangular to polar form is summarized as a special mathematical result of special importance to electrical engineers is the fact that exponential of j theta equals cosine of theta plus j sine of theta. The sine and cosine functions can be written in terms of exponential as shown. A time-dependent sinusoidal signal is defined as x of t equals a cosine of omega naught t plus phi, where omega naught is equal to 2 pi f naught, as given in the second form. We say that the signal x of t swings between plus minus a with a radian frequency of omega naught. The frequency f naught equals omega naught by 2 pi is the oscillation frequency in cycles per second or hertz, and phi is the phase angle in radians. The animation of sine of x is shown with x-axis as the phase angle in radians and y-axis as the corresponding amplitude value of the sine function. The second animation is for different amplitudes. A time-variant, periodic signal with amplitude, a equals 20, is shown next. Here, omega naught equals 40 cycles per second and phi equals minus 0.4 pi radians. Note that the time interval between maxima, minima, and zero crossings is the same. To have a relationship of frequency and time period, we can write the relation, which is x of t equals x of t plus t naught, where t naught is the time period, or the time after which the signal is a copy of itself. For a single sinusoid, we can relate t naught to f naught by considering a cosine of omega naught into t plus d naught, plus phi equals a cosine of omega naught into t plus phi. For periodicity, omega naught multiplied with t naught equal to 2 pi. Since omega naught equal 2 pi f naught, this brings us to the inverse relation between t naught and f naught. For a 40 Hz signal t naught equals 0.25 milliseconds as shown. Another example of signals having fundamental frequencies equal to 200 Hz, 100 Hz and 0 Hz are shown. Note that the period of 200 Hz signal is half of the 100 Hz signal. The phase shift of the sinusoid moves the waveform left or right on the time axis. Consider a triangularly shaped signal S of t with piecewise continuous definition on the right. Its delayed version is x1, t, equals s of t minus 2. The advanced version is s of t plus 1. These are obtained by putting t equals t minus 2 and t equals t plus 1, respectively. Please see how the start and end of ch signals are shifted. In general terms x1, t equals s, t minus t, 1, is delayed in time relative to s of t, if t, 1 greater than 0, and advanced if t, 1 less than 0. The cosine signal with positive peak at t equals 0 is shown. For a delay of t, 1, the function can be written as cosine of omega naught t minus omega naught t1. Implies negative phase shift, that is, phi equals minus omega naught multiplied with t1. For a given phase shift, we can turn the above analysis around and solve for the time delay, that is, t1 equals minus pi by omega naught. Since t naught equals 1 by f naught, we can also write the phase shift in terms of the period. The value of phase shift that lies on the interval pi to pi is known as the principal value. An example is shown where a time delay of 10 milliseconds with a period of 3 milliseconds means that we have delayed the sinusoid 3 full periods plus 1 millisecond. Hopefully, you have enjoyed the presentation, and have contributed to or refreshed your knowledge. In the next presentation we will be showing MATLAB code for sinusoidal waves. Stay safe. Please like, subscribe and share with friends and class fellows.